Now, in this video, we will going to discuss about the stress-strain relations. So, here of the stress-strain relations or diagram for ductile material. So, first we are going to take up the experimental work of how to conduct a tensile test on the ductile material specimen using universal testing machine. So here we have a specimen wherein you have the D0, the diameter, that is L0 is the gauge length, and D0 is the original diameter of the specimen, and then P is the axial tensile load applied. The stress-strain relation on a ductile material is obtained by conducting a tension test in the laboratory on standard specimen. So the following informations can be obtained from the tension test. So what are all the information we are going to get? One is the proportional limit, then the elastic limit, then the modulus of elasticity, yield strength, ultimate tensile strength, modulus of resilience, and modulus of toughness, and percentage elongation, and the percentage of reduction in area. So these are all the informations which we can be obtained by using the tension test. So the cross section of the specimen can be either it can be a circular or the square or the rectangular cross section. So initially, so this is the procedure what we need to do before conducting the tensile test on the specimen by using universal testing machine. First, initially what we need to do is the gauge length is marked on the specimen and the initial dimension of D0 and L0 are noted before starting the test. The specimen is then mounted on the universal testing machine and gripped in the jaws. So an extensiometer is fitted to the test specimen which measures extension over the length L0. So it is then subjected to an axial tensile load which is increased by a suitable increments. At the regular intervals after each increment, the amount of which the gauge length L0 increases, that is the deformation of gauge length, is obtained from the extensometer. The procedure for measuring the tensile load and the corresponding deformation is continued till the specimen fractures or breaks into two pieces. The tensile load divided by the original cross-sectional area of the specimen gives the stress, while the deformation divided by the gauge length is going to give you the strain in the specimen. The values of stress and the corresponding strains are used to draw the stress-strain diagram of the material tested. So this is the typical stress-strain diagram for the ductile material. So here we have O to P, then E, upper yield point, lower yield point, then you have the ultimate, then the break stress. And this is the true stress-strain curve. And this is the nominal or conventional engineering stress-strain curve. So this is a typical stress-strain diagram for ductile material like main steel, where P is the proportionality limit and E is the elastic limit, YU is the upper yield point, YL is the lower yield point, U is the ultimate strength, and B is the breaking point or the rupture strength. So once we take up the proportional limit, so from O to P, the curve is a straight line, and after the point P, the curve begins to deviate from the straight line. The Hooke's law states the stress is directly proportional to strain. So that is from O to P. So this is from O to P is the one which will be called as the proportional limit. Then Hooke's law holds good up to the point P, and this point is known as the proportional limit. It is defined as a point at which the stress begins to deviate from the straight line. And then we have the elastic limit. Up to the point E, the material regains its original shape and size when the load is removed. It means that the material has elastic property up to the point E. This point E is slightly beyond the point P and is known as the elastic limit. So elastic limit of the material is defined as the maximum stress without any permanent deformation. So then comes the yield strength. If the material is stressed beyond the point E, the plastic deformation occurs and the material starts yielding. On the removal of load, the material will not able to regain its size and shape. So this is the point what we are talking about, the upper yield point, where the material will start deviating from the elastic limit and where it will start getting into the permanent deformation. So this will go to the plastic range. So on the removal of load, the material will not going to regain its original size and shape. Then beyond the point E, the strain increases at faster rate up to the point YU. That is, there is an appreciable increase in strain without much increase in stress. Point YU is called the upper yield point. Then the curve drops down to YL, that is the point YL, which is the lower yield point. At this stage, the stress remains same, but strain increases for some time. This phenomenon of increase in strain without any appreciable increase in load is called the yielding. So then the material will start yielding to the load what you have applied. So for most of the materials, YU and YL are very close to each other, and thus the 2 points are considered as same. So that is the reason why we say just the yield point. Then yield strength is defined as the maximum stress which is marked increase in elongation occurs without increase in load. So next, the ultimate strength. After the lower yield point YL, plastic deformation of the specimen increases, that is ductile extension takes place. During the extension, the cross-sectional area decreases uniformly all over the length, but such that the volume remains constant. At the point U, the load and the corresponding stress attains its maximum value. Point U is called the ultimate point, and the stress at this point is known as ultimate or the maximum stress. The ultimate tensile strength is the maximum stress that can be reached in the tension test. Then the breaking point. After the maximum load is reached, local yielding takes place and a neck or waist is formed. As the cross-section area decreases considerably, the load carrying capacity of the specimen reduces, and hence the portion UB, the strain increases for decrease in stress. Even though the nominal stress is decreasing, the actual, that is the true stress, which is equal to the load divided by the cross-section area at neck, will continuously increasing. At the point B, the specimen breaks. The stress at this point is called the breaking strength or the breaking stress or fracture stress. And the corresponding load is called the breaking load. The breaking strength is slightly lower than that of the ultimate tensile strength. The stress at which finally the specimen fails is called the breaking point. The nature of fracture of the mild steel is cup and cone arrangement. The stress relations for the brittle material. So we are going to take up the stress strain for the brittle material in the next video. If you like this video, you please subscribe to my channel. Thank you.